Okay, so actually, the first, those are the problems. Is the problem from Willard book. This question number 26C or from page 196, and mainly this deals with the connected spaces. Okay. Okay, so what is the first problem? It says that a connected Tychonoff space having more than one point has C is greater than equal to C. C means cardinality of real numbers or cardinality of continuum. Okay. So what is the Tychonoff space? Definition is completely regular plus T2, right? Can you hear me?
Yes, sir.
So can you please try these two problems quickly? Since you two are here, so maybe you can try. And this may be like you have exam on coming Wednesday, so maybe it will be a practice session. So can you please try these two problems? I've given everything, like it's a Tychonoff means a completely regular space, which is T2. So it's also given that if it has more than one point, then it has at least C elements. The idea is the image of a continuous function or continuous image of a connected set is connected. So idea is this one. Continuous image of a connected space is connected. In fact, you have to find out a continuous function f from x to r. Okay. So can you quickly see which continuous function will take place here? I've given everything. It's completely regular, it is Hausdorff, and so what you all need to do is that you have to find out continuous function from x to r. Yes. Are you following me?
Yes, sir.
So see, if you should respond, right? So what is the definition of a completely regular space? What do you mean by completely regular?
Sir, we can separate 2 points by a continuous function.
2 points or a point and a closed set?
As you said, a point and a closed set.
And you are given a Hausdorffness, right? Now you assume that x has more than one point. Let x has more than one point, or cardinality of x okay. So suppose and take x and y belongs to x, where x and y are not equal. Then by Hausdorffness, what we can say? There exist ux and uy, right? Actually, we do not need those, but I want a neighborhood u of x, so that x minus u is non-empty, and that is why I am using the Hausdorffness to find out that neighborhood. So there exists neighborhood ux and uy such that their intersection is empty and x belongs to ux, y belongs to uy. Okay? Now you see, now you consider the set, say B equal to x minus ux. This is closed, right? Closed, and x does not belongs to B. Now can you see, you have a point x and a closed set B, which is not in B. So now can we apply this definition, the complete irregularness? Yes, please produce me the continuous function. Since your exam is on ONS, right? Is it fixed? As some of you requested for the exam after 10 or something like that, I don't know, but everything will be up to you and sir, I don't know. Anyway, so can you follow me? What to do next? I have given everything. Now you have to produce a continuous function. क्या हुआ, क्लास करना है कि नहीं करना है? Let me finish to my task. So you have x and B closed set which is disjoint from x, and your space x is completely regular. So therefore, by the definition, there exists a function f from x to, you can say, 0, 1, such that fx equal to 0 and fy equal to 1 for all y belongs to B. Now you see, x is connected and f is continuous, therefore fx is a connected subset of of 0, 1, or in fact it is a connected subset of R. You can take this space as your R. Okay, it's a connected subset of R. Therefore, fx is an interval which contains 0 and 1, right? And therefore, you can say this set 0, 1 is contained in fx, right? Therefore, cardinality of fx greater than equal to cardinality of the closed interval 0, 1, which is C. Now cardinality of x is always greater than equal to cardinality of fx. Therefore, so you have cardinality of x is greater than equal to c. That was the problem. Okay, clear?
Yes.
Yes, sir.
See, you should respond and try to solve them. Actually, in the exam also, sir will ask you this kind of problems, and maybe you can get some common problems as well, which he has given during the classes, and he told you many things, right? That you will get more than 30 marks problems from connectedness, compactness, and all those. So please follow him and try to solve the problems which he has given in the class. Since it's an offline exam, maybe he can give something from there also. See, in the online exams, questions are always difficult, and every professor follows that, like to set a difficult question paper. Anyway, so now look at the second one. This is not much easy, or it's not that much trivial, but can you have any idea how to proceed for this problem? Actually, the idea is same. We will produce a continuous function. So first of all, we produce that. We first prove that if we have a connected separable metric space X, then its cardinality is at least C if it contains more than one point, and then we will prove that it is strictly less than C, means there is some injection from this space to the space of real numbers, or R power n, which you can say, which has same cardinality as R. Okay. So for 2, okay. Again, suppose what you are given, X is separable, connected, and in fact it's a metric space. So you can say X comma D. Okay, it's separable and connected. So let us start with the connectedness first. So from connectedness, what we can say? You see, now we first fix an element y belongs to x, and we assume that x has more than one element. Okay. Now define a function f from x to r by fx equal to distance of y comma x. Right? Clear? Is it continuous? It is continuous, right? Now you see, what is the value of fy? This is dy comma y is dy comma r. So dy comma y equal to 0, right? And what the problem is, and they have assumed that x has more than one element. So if we take x naught from x minus y, then we will have d of x comma x naught is greater than 0, right? By the definition of metric space. So therefore, if we consider, if we take this element as b, then what we will have, fy equal to 0 and fx naught equal to b, right? Right? Now f where 0 is strictly less than b. Now you see your function. Okay, maybe we will solve this problem later. Let me continue this one. Okay, so now you have a function f on a continuous function on a connected space, Therefore, fx is connected subset of what? Connected subset of R. Therefore, fx is what? It's an interval.
Interval.
Yeah. So since it's an interval containing 0 and
0,
b, right?
B.
Therefore, what we can say, this interval, the entire 0, b interval is a subset of fx, right? So that what we can say, cardinality of 0, b less than equal to cardinality of fx less than equal to cardinality of x, right? This is C. So we have got one inequality that cardinality of x is greater than equal to C. Fine. So connectedness gives us this condition. Whenever your metric space is connected, then this condition holds. Now we will use the separability to prove the other inequality. Okay. So now let X be a separable metric space. Okay. So actually, okay. So now tell me one thing. You consider R power n. What is the cardinality of this set? Can you express R as 2 power n? There is a bijection between R and 2 power n. 2 power n means the power set of n. Right? Right? Huh?
Yes.
Therefore, so from here what we can say? This is 2 power n. Right? Therefore, it is 2 power n cross n, right? What is the cardinality of this set? Same as cardinality of n. Therefore, this two set has same cardinality, 2 power n, which is same as here equivalent means the sets have same cardinality. Okay, by this I mean that these two sets has same cardinality. Fine. Now actually we will see that there exists, we claim that there is a bijection, or sorry, not a bijection, there is an injection map. Will it be fine if I produce an injection map? A from x to r power n. Will it be fine if I produce an injection map from x to r power n? Yes, no? It's a set theoretic argument. What does injection mean? Injection means this set will have a copy. Means r power n will contain a copy of x, and therefore you can say in some sense this fx which has same cardinality as x and fx subset of r power n. So in terms of cardinality, this is same as c. So cardinality of x will be less than equal to c. Fine. If I am able to prove that there is an injection from x to r power n, then we are done. Clear? Anyway, okay. Now let x belongs to x. Okay. First of all, we need to fix an element. Okay, not fixed. First of all, I have not assumed anything about separability, right? What is happening? Anyway, so let B be a countable dense subset of X. Okay, since because you are given that X is separable. Now, for X belongs to X, define a map. Define a map F from X to R power n by F of X equal to D of X comma A X D of, how can I explain? So actually I want to explain the elements in this way, where the Fx is equal will be of this form D of X comma A for A belongs to B. Is it clear? Or you can say R power B. Fx2, instead of writing this, take Fx to R power B, because R power B and R power n will have same cardinality as A B is a countable set, right? Therefore, you take Fx this kind of elements. So this kind, so your Fx will be an element of R power B, means see what is your R power B? This is R cross R and so on, right, up to B, up to the cardinality of B. Okay, and actually we are taking the elements like this were indexed over the elements of B. Is it clear? Have you got the function? What I said here? Yes, no? Is it clear? The function I have given. If it is not clear, tell me, I will explain. So, but in the to understand this function, this is actually dx comma a1 dx comma a2 dx comma a3 and so on, dx comma a4 and so on, dx comma an and so on. Actually like this way, where your set B is this one. Is it clear now? This is your fx. Okay, let me take, this is your fx. Let me take your B set as A n belongs to n. So this is a dense subset of in X. So now is it clear? Okay, you are alone. Means the left